joining, we will take another. So almost 262 participants have registered for this FDP. This is our FDP, which is funded by the AICTE.
Yeah.
Under the ATAL program. So it is a 6 days long online FDP. In the evenings are. So that the academicians and the industry people and the research scholars, they can learn and explore more about and specifically AICT the semiconductor. So since the government is focusing towards the semiconductors, that is the reason.
Okay, yeah.
Just let few more people join, then we will start.
Okay.
So, and a resource person for the another session after your Dr. C. Ramachandra, he is also there. Good evening, Ramachandra sir. Maybe connect.
Good evening.
He's here.
Good evening, Dr. Pooja Agarwal.
Yeah, good evening, sir. So we are having two sessions today, one from Professor Lee and another from Dr. Ramachandra. Dr. Ramachandra gave the session on the second day also, and the participants, it was a very engaging and the informative session. So people are joining. I think we can start at 6 p.m. Can we start, Professor Lee?
Oh, no problem. Anytime.
Yeah. Ishika and Ayush, please take it forward.
Sure. Good evening, everyone. A very warm welcome to day 4 of this 6-day online ATAL Faculty Development Program on Vacuum Technology in Semiconductor Manufacturing and Packaging, Innovation, Applications and Challenges, organized by the North Cap University, Gurugram. As we progress further in this program, we continue to explore the significant impact of vacuum technology in semiconductor manufacturing. Yesterday, on day 3, we had two highly insightful sessions focusing on vacuum chambers and system design and vacuum technology in IC fabrication.
In the first session, Professor V.V. Rao provided us with an in-depth understanding of vacuum chamber construction, covering system optimization, material selection, and pressure regulations essential for semiconductor applications. His sessions helped us comprehend how well-designed vacuum chambers contribute to efficiency and precision in microelectronics fabrication. Following that, Professor Mohammad Javed Siddiqui guided us through vacuum technology in IC fabrication, offering insights into how vacuum environments play a critical role in semiconductor device manufacturing. His discussion covered vacuum pumps, contamination control, and the role of vacuum in achieving high-performance integrated circuits.
As we move forward, today's session will take us deeper into vacuum technology in semiconductor packaging and etching processes under vacuum conditions. Our expert speakers will provide valuable insights into how vacuum is utilized to enhance durability, reliability, and performance in semiconductor devices. Their expertise will help us understand the latest advancements and industrial challenges shaping the future of semiconductor technology. Let's begin day 4 with enthusiasm, curiosity, and a shared commitment to learning.
We are honored to welcome Professor Shangchen Li, professor at National Tsinghua University and CEO of Seixiang Foundation of Science and Technology, Taiwan. Professor Li has published over 360 journal and conference paper in areas such as computational solid mechanics, 3D IC system integration, nano-micro device reliability, and MEMS technologies. He has led over 90 projects related to flexible OLEDs, package simulation design, and 3D IC reliability estimation. as an associate director editor for IEEE Transactions on Compounds, Packaging and Manufacturing Technology and Microelectronic Reliability. His research focuses on electronic packaging reliability, stress-induced reliability in high-power modules, and interfacial fracture analysis in thin films. Today, he will provide insights into how vacuum technologies revolutionizing semiconductor packaging, ensuring high-quality market manufacturing, reliability, and efficiency. Without further ado, we invite Sir to take the virtual stage and share his expertise with us.
Okay. Thank you for
Welcome,
your
sir, once
introduction.
again. The stage is yours now.
So I need to share my slide, right?
Right, you can share the slide.
Okay, no problem. Yeah. Can see my slide?
Yeah, we can see your slides.
Yes, sir.
Okay, now I'm start my talk. Good evening, everyone. I'm Professor Changjun Li, come from Department of Power Mechanical Engineering, National Tsinghua University, Taiwan. Today we will talk about the semiconductor manufacturing and the packaging innovation application and the challenge. Actually, in this talk, I will focus on the outline here. The first part is I will want to introduce the development and the current status of the fan-out packaging. As you know that the at current the fan-out and the 3D IC packaging are the popular the framework of the packaging structure, and the fan-out packaging we expect they will be here popular more than 10 years. So so understanding the fan-out packaging is very important. Even for now, if you join the international packaging conference, the fan-out packaging and the 3D IC packaging are the most important topic here. So this is why I would like to introduce the development and the current status for fan-out packaging. The next topic I will want to introduce the development trend and the key technology of 3D IC packaging. Just as you know that fan-out packaging just for the some application of the semiconductor chip, but for 3D IC packaging, actually for memory cube, memory stacking, memory chip stacking. Now 3D IC packaging is very important. And then I will introduce the development of the current status of the heterogeneous integration packaging technology. Because this topic is very important, just we know that we want to integrate the chip with the different function within the packaging. Even for SoC system on chip, the system on chip now we will want to split into several smaller chip. Each chip have the different function and use the packaging technology integrate them together to become a system. Through the packaging technology, the concept can be worked. This is why we want to introduce the heterogeneous packaging technology here. By using the packaging technology, the thermal stress and the reliability, the thermal stress within the structure can be reduced, and the packaging reliability and the lifetime can be enhanced a lot. In the last part, I would like to introduce the several vertical design and analysis case for 3D IC packaging. This is all in today's the talk. And I will back to my previous slide. Actually, in this slide, just my self introduction. When I joined the NTHU, I work in the TSMC, be a principal engineer in R&D department, and then go to the and then back to the school, and be a professor, and now I'm CEO and the Zhiqiang Foundation of the Science and the Technology. And now in this year I received the ASC fellow, and the next year I get a STNM fellow here, and I also IEEE CPNT Associated Award get this award last year, and Outstanding Research Award from our government, National Science and Technology Council. And I serve several journal associate editor here. This is all of this is the brief introduction for myself. Here I just show you my research area. The first item is advanced packaging technology, and then the mechanical design and the integration of 3D IC system, and the backend of line process enhancement and the reliability investigation of narrow micro device. And the next part is the computational solid mechanics. So also, this is why I in the power mechanical department, because my core technology is the core background is the solid mechanics. Okay, this is my introduction for myself. Now I will go to the first part here. In this slide, I just show you the typical PCB assembly in electrical product. As shown in this figure here. In this figure, you can see that this is a PCB board, right, or motherboard. In this board, you can see that so many semiconductor devices here are mounting here, and so many IC chip embedded or molding by the impassive material and mounting on the board. And we select one IC here, for example here, and we cut the cross section along the red line, and you can see this the cross section so far here. And first, we introduce the right side cross section. This is a typical packaging structure here, and you can see that we have a leaf frame here, and at the center of the packaging, the IC chip B is placed here on the leaf frame, and through the wire bonding and wire bonding technology using the golden or copper will connect the I/O of the chip to the metal leaflet. Through the wire bond technology and the wire bond technology and the leaflet structure, the electrical power and the signal can input and output through the path. And as you know that the IC chip is easy to fail because they always in the fab, right? Cannot go to the terrible the environment. So this is why we want to embed the IC chip with the molding compound. The molding compound usually is the impassive material, just the black material here. Okay, and in the early stage of the semiconductor, the packaging mounting the PCB is by the through-hole technology. It means the leaflet at the end of the leaflet, it's directly through the hole and use the solder assembly with the PCB. But by this way, the routing of the line, the spacing of the routing line reduce a lot, and we cannot incorporate additional device here. And so this is why the through-hole technology now do not use here. And now we use the surface mount technology. By this way, the solder material or solder paste first is pressed here, and then light and place the package structure on the PCB board, and use the reflow technology, reflow process, and heating the temperature higher than the melting point of the solder material, and then cooling down to the room temperature, and then finish the mounting the procedure here. But the right side, such kind of the right side packaging structure, just suitable for low I/O pin or low I/O the leaflet here. But as you know that the IC chip will be would like to have a larger I/O number and the more function, thinner the chip. So by this approach, the high density I/O cannot mounting by such kind of package structure. This is why we will transfer and develop another kind of the package structure here, as shown in the left side here. In the left side, the cross section of the package structure, we can find that the IC chip A have the smaller solder bond, and the solder bond is not at the edge of the chip. Now the solder bond is always under the bottom area of the IC chip and arrangement by the ball-green array, the type, ball-green array type. And by this the arrangement assembly to the packaging substrate. The packaging substrate, the upper side of the packaging substrate, actually the ball pitch is smaller and finer. And the bottom side of the packaging substrate, the ball pitch is larger and extensive. Why? Because the I/O pitch finally need to compatible with the PCB pitch. So the packaging substrate look like a switch, light switch. The upper side have the redistribution layer with the finer pitch. The bottom side have additional redistribution layer with the larger ball pitch. So this is why I call it as the switch here. And by this way, the IC chip can mounting to the PCB, and this is the mainstream and the mainstream of the packaging structure here, BGA, ball-green array type the assembly. Okay, and why we need to have the but by such the structure, you can see that the chip, the coefficient of the thermal expansion for the chip is about 3 ppm per degree C, but for packaging substrate, the material is always the organic material. The organic material is about more than 20 ppm degree C. So it's about 7 or 8 times than IC chip. So when temperature increase or decrease, will induce a lot of the CTE mismatch, CTE coefficient of thermal mismatch between the chip and the substrate. So by this at this condition, the large shear force will apply to the solder bond, and finally the solder bond and the solder joint will crack. This is the reliability issue of the solder ball. So when we talk about the packaging technology or solder joint reliability, just focus on how to enhance or protect the solder joint or solder ball from far away the crack. Okay, this is the best concept for the packaging, the design and the reliability, the issue here. And next, I want to talk about the patterns from the pattern impact the semiconductor packaging. Even there are many important patterns such as the free chip, TSV. TSV is the important component within the 3D IC packaging. The full name is the through silicon via. TSV, through silicon via. Here I think that The following there has four impacts the semiconductor packaging the most. The first is lead frame. Lead frame we have shown here in the slide here, right? In the previous slide here. And the next is the organic substrate with a solder ball green array. And the next is the fan-in wafer level packaging. Fan-in wafer level packaging, okay, or wafer level CSP. Next is a fan-out wafer level packaging or panel level packaging here, okay. In the first pattern for the lead frame, I want to introduce here. This is a pattern. Wow, this is a lead frame, right? This lead frame. If a lead frame do not curve, the end do not curve, it means such kind the lead frame assembly we need to through hole technology, not the surface mount technology. It means we have so many holes in the PCB. This is not good. So this is why the lead frame will be curve here, have a curve here. And in this slide, you can see that the chip is placed at the center of the package structure using the wire bond connect the pad, IC pad to the lead frame. And the right side is the top view of the lead frame structure. And the number 18 is the location of the IC chip. And in this slide, show you the other viewpoint of the such kind of package structure. Chip here, chip at the center, and the wire bond connect the I/O and the lead frame. And the top and the picture in in this slide, I point out here. You can see that we use the gold ring lid. By this way, we do not use the through hole, just the surface mount technology. And by using this figure, you can see that the I/O and the lead frame is always at the edge. So this is why this kind of the package structure is suitable for low I/O pin. Okay. Compare the left bottom side of the package structure. Okay, lead frame different, right? Lead frame configure is different. The right button is a through hole lid here. Okay, and we have jet lid here. Jet lid here. The jet lid, the using of the jet here is one to reduce the packaging heat area. Okay, the next I want to introduce the substrate and the solder ball to fan out the chip, the circuitry here. Okay, this patent is filed by the Motorola in the 1992. The packaging, this patent is focused on the switch. I call switch. Actually, this is a packaging substrate here. By using the packaging substrate, the ball green array can be formed on the packaging structure. The packaging substrate, the top side, the upper surface is the finer and the finer width and the finer spacing of RDL. But the bottom side of the substrate become larger pitch larger pitch and assembly to the PCB. Okay, this is the pattern. I think is very important because just I said that most of the package structure until now still use such kind of packaging technology here. Here I give you some example here. Please reference the figure in the right side of the slide. The first I point here is the well-bound configure packaging structure, and the packaging substrate. Here, the upper surface is well-bound, and the bottom side is the solder ball array. So by this way, we the chip assembly to the PCB, and in the bottom bottom figure, you can see that the chip do not use the wire bond. The chip use the free chip technology. Free chip mean the solder ball is smaller than the solder than the another kind of the solder ball. Have a smaller solder ball and a larger solder ball. The free chip mean a smaller solder ball here, and because chip is because the chip have a smaller solder ball, the smaller solder ball under the CD mismatch, the stress is easy to crack. So such kind of free chip technology will fill in the underfield around the free chip ball. By this way, the free chip can be protected, and the stress distribution will be shared by the underfield. Okay, so the bottom side of figure is is applied to the high end the packaging the structure. So the packaging technology, the chain of the packaging technology is the smaller solder ball, higher I/O density, and more function. This is the trend. Okay. And next, I would like to introduce the third pattern here. The third pattern is a fan-in wafer level packaging. The wafer level packaging. The difference with the wafer level packaging with the traditional packaging is that the wafer level packaging is mean I need to say like this way. Traditional packaging, the first step is that the chip is dicing from the wafer, become a single chip, and we use each chip is then packaging, and the then packaging become a packaging structure. But the wafer level packaging is mean before the dicing the procedure of the chip, the wafer packaging directly. After packaging than dicing. So difference, okay, understand? I repeat again. The traditional the traditional packaging, the technology, the chip first dicing from the wafer and then packaging. But the wafer level packaging, especially for fan-in, such kind of wafer level packaging is mean the wafer packaging first and then dicing. After dicing, we finish the packaging for the chip. Okay. And why we call it the fan-in? Here, this is the wafer level packaging. The first pattern of the wafer pack the wafer level packaging. I remember when I was a graduate student about the 2000 here. Oh, wafer level fan-in wafer level packaging is very popular, with as shown in this pattern. But why this is fan-in? As you can see, the bottom side of the layout here, you can see that the I/O of the chip, the I/O of chip is close to each edge of the chip, and after RDL, after redistribution, become a ball green array. The bread duct mean the location of the solder ball. It's close to the central area of the chip, and in addition, you can find that the area of the ball green array is the smaller or equal to the chip. If such kind of arrangement, we call it as the fan-in packaging. Fan-in packaging. Fan-in. I repeat again. The concept is very important. The area of the ball green array is smaller than chip size, smaller or equal or smaller than the chip size. Such kind of packaging, such kind of ball green array structure, we call it as the fan-in, the packaging, the structure. So you can from my talk, you can understand such kind the packaging structure, the I/O number cannot so much, right? If we have additional I/O number here, finally, the condition is that the ball green array is larger than chip size. This is for high density I/O, the case, right? But I just say that the I/O, high density I/O is the trend of the IC chip, right? So for packaging structure, now we always find that the ball green array, the area size is larger than chip size. So at this condition, we call it the fan out. So this is why the structure show here is a fan-in. Another kind is a fan-out. Okay, I just early to talk about the definition of the fan-out. Okay, for fan-in packaging, we do not use the underfill. Underfill used in the free chip technology. The the solder ball are directly mounting on the packaging substrate or PCB substrate. But by this way, the large CT mismatch is between the chip and the substrate and induce the largest stress on the solder joint. So actually, we will insert a stress buffer layer close to the chip side and to protect and share the pattern the stress of the that will apply to the solder joint. Okay. And in this slide, I just show you some the electrical product that will use the wafer level CSP. Okay, I do not go through the details. You can see that the wafer level packaging, the I/O pin count is smaller or equal than 200, and the small size cannot use the larger chip size here, and the low cost, low end, and the low profile, and the high volume application here. And in the smartphone and the tablets and the wearable NB and the medical application can be used the wafer level packaging. So if you watch the iPhone or smartphone, you can see that so many packaging structure within the iPhone here or smartphone here. For iPhone 6 Plus, there are 26 wafer level CSP here. Okay. Actually, because of the die shrinkage, and the chip have more functionality. It means more I/O pin count, more input or output pin count, and the requirement of the system in packaging. Okay, as shown in this figure, here, the wafer dicing become dicing as the chip. This is one chip. Continuous shrinkage, but we have a need to more function here. And then, so for example, chip A and the chip B mount packaging together within one package here. This is multi-chip modules. And by this way, you can see that the ball green array size is larger than total area of the two chip. So such kind the packaging structure, we call it as the fan-out packaging. Okay, the fan-out packaging can divide into two kinds. One is the wafer, another one is the panel. This is mean the manufacturing size. Okay, during the manufacturing. If we use the carrier is a wafer, we mean the fan-out wafer level packaging. If the temporal substrate is a panel size, we call it a fan-out panel level packaging. Okay, so this is the pattern we show you here. Okay, fan-out wafer level packaging applied to such kind the product here. I do not go through the detail. And this is the pattern. The first the fan-out packaging pattern here. As I near is the inflating technology in 2000s years. Okay, as shown in the main figure of the pattern, this is the chip. The chip size is smaller than, the ball green size is larger than chip size, and do not have any substrate. Just use the RDL. Here call is the dielectric here, and the metal wire. Such kind of the structure is the characteristic of the fan-out packaging structure. And this is the top view for the pattern file here. And in this slide, I just show you again the detail of the fan-out packaging and the fan-in packaging. The top figure is the fan-out packaging. As I show you here, the ball green array size or area is larger than chip size. Okay, and in the fan-out packaging, we do not use the packaging substrate as shown in the previous slide. We just use the RDL directory, RDL redistribution layer, multi-layer redistribution layer to fan out the metal well and the precision of the ball green array. Okay, and compare this the fan-out package figure. Bottom side is the fan-in packaging. You can see that the ball green array size is always equal or smaller than chip size. Okay, but when we use the fan-out packaging, we can check the chip is non-good die or not. If the die have failed, we do not want to the chip packaging. This is waste the cost, right? So it has better the wafer level the year, and is tend to multi-chip the framework. Okay, and can be embedded the integrating passive the device more than one RDL, usually more than 2 or 3 layer here, and higher pin count. Okay, because such kind of profile is thinner, so it has better thermal performance and the electrical performance, and they can be go for system in packaging and the 3D IC packaging. Okay, and higher level reliability. So fan-out packaging have the such high many advantages. So this is why we expect such kind of packaging structure can be continue more than I guess the more than 10 years. The fan-out packaging still here. Okay. So again, in this slide, the upper part is the fan-in packaging. The bottom part is the fan-out packaging here. Okay. Again, the upper part, portion is the fan-in packaging, and the bottom portion is a fan-out packaging with the 2 chips within the packaging structure. If the packaging structure, if one packaging structure has 2 or more than 2 chips here, we mean such kind packaging is the multi-chip modules. Actually, for advantage technology, the definition for advanced packaging is then the packaging structure need to at least more than 2 chips within the packaging structure. Okay. So I have go through in this slide, I just want to show you the fan-out packaging, the advantage. Low cost, low profile is mean thinner, and eliminate the substrate, package substrate. We do not have package substrate here, and do not have the wafer bumping and the reflow, underfill, and the cleaning flux. It means the smaller bump and underfill do not here. Okay, but we have additional structure, just the ideal here. By this way, we have better electrical performance and the thermal performance, and easy to go for SiP and the 3D IC packaging. Okay. By the previous introduction, actually, this is the major trend for the packaging technology. First, from the left to the right side is from the traditional to advanced. PBGA, free chip BGA, and the wafer level chip scale packaging, and the fan-out wafer level or fan-out panel level packaging. And the bottom side just lists some specific spec for the solder bond pitch and the bond size here. Sorry. And now I will want to introduce the manufacturing process of fan-out wafer level or panel level packaging. Actually, from the viewpoint of manufacturing procedure, the fan-out packaging can divide into 3 kinds. The first is the chip first die up. The die up means the transistor is face up. Transistor is face up. Another kind is the chip first, but the chip die. The die down is mean the transistor, the face having the transistor is face down. And the third kind is the chipless. The chipless is mean RDL first. Chip first and the chipless here is mean the chip in the process is in the beginning just place the chip in the carrier. Chipless is mean the chip just press on the packaging is almost at the end of the process. So chipless is mean we would like to fabricate the RDL, the structure first. So the advantage and the disadvantage for the three process, I will introduce the detail later. Now I will introduce the chip first, or die down, and the die up. Most of the fan out, wafer level, and the panel level packaging in the manufacturing today use either one of these formation for portable, mobile, and wearable products. This reconfigure carrier is either wafer or panel. Okay? And the chip first die down. Such kind of process is also called embedded wafer level ball green array. This is the licensed by the Influence the company. Okay, and now SE status status chip pack and ST microelectronics. Okay, so I have this license here. And EWB is used to packaging in the such kind of application here. And here in this slide, I just show you the process flow. Actually, we will like to prepare the non-good die. Okay, here first. For example, this is wafer. After testing, we will select the good die. The cross-section is here. This is, for example, the chip fabricated from the TSMC and the UNC. And we get the chip here. And then we will prepare the temporary carrier. The size is either wafer or panel. Okay. The panel size is always larger and larger than wafer because the cost issue. And then we will prepare the two-side tap, thermal release tap. And then each non-good die press to the wafer and the panel. Okay, our desired the location. Okay, sorry, we have the taper here, and this is not good. And the next step, we will fix in the impassive molding compound. Okay, and remove the carrier and the taper. And at this moment, the I/O will be exposed to outside, and then fabricate the RDL and press the solder ball. After that, dicing become the single chip here. Okay, this is very important. Okay, this slide show you that the RDL. Sorry, this slide show you that the chip first die down is the procedure is very simple, but this is have two issue here. One is that when we fit in the impasse molding compound at high temperature, the thermal release tap, the adhesion will be will become weaker. It means after the EMC step, the chip will have the moved a little, will move its location a little. This is not good. Why? Because our design for the RDL is focused on the desired location. If we have the die shift issue, the totally will be fail. The totally of the wafer and the packaging will be fail. So the die shift is the reliability issue that need to be overcome here. So next, I will show you if we do not use the thermal release tap, another option is to use the die attach film. But this process need to additional cost and step here. Okay, and during the process, the wafer carrier and the panel level and the panel carrier, because of CT mismatch, the wafer will be warpage. The panel carrier warp larger than wafer because of the size issue. The warp is not good. Why? Because we define the RDL width and the spacing. The tolerance is the phi pitch and the phi spacing is impossible. Why? If warpage issue cannot be overcome, this is we will have a misalignment, the problem here. So warpage issue is the most concern when we when you studying the packaging, the paper, journal paper, so many paper now just discussing the warpage issue here. This is another issue for the chip first, the fan out packaging. The issue is that as shown in this process in the slide, you can see that the non-good die chip placed on the carrier in the beginning of the process. During the thermal cycling of the process, the step, the non-good die finally maybe have the issue to fail. This is not good, right? So actually we have such issue, but the process is very cheap among the three types of the fan out the procedure. Okay, this kind is very cheap. So in this slide, I just show you the inflating the embedded wafer level ball green array. The picture here, EWB. Okay, I do not go through the detail. This is the picture of the wafer size. Okay. And actually, the chip first, the die down RDL is fabricated by the thin film method. The process is shown here. For example, this is die. This is die, a non-good die after molding, and at this moment, the surface of the pad is posed on the outside, and then we spring coating the polymer, for example, PI, PCB, and PBO material, and then photoresistant and litho and etch the polymer and sputter C layer and the barrier and the photoresistant again, and litho again define the location of the copper line, and then copper printing process, and remove the photo resistant, and repeat the procedure. You can fabricate the RDL1, RDL2, and finally create the solder ball look and its location. Okay, actually the fan-out packaging have applied to the Galaxy S7 the product, and this is the PGB, the top view, and you can see that I show you here have the fan-out wavelet packaging here. Okay, this is fan-out packaging. Okay, embedded wavelet packaging from the infilling, non-good die, RDL, and the ball grid array. Okay. This slide just show you that the one fan-out packaging can cooperate with the two non-good die. Okay. And then I will introduce the chip first, the die up the process. Sorry. Actually, when we prepare the die first, the die up the process from the viewpoint, from the side of the chip, the chip come from the wafer, right? Dicing from the wafer, and then we will have some process here. We will form additional contact pad on the original pad. Okay, it means the pad now become the thinner, right, and the hider. Okay, and between the contact pad, we have the polymer material here. Okay, this is first the step, and when the IC chip is ready, then again, first the temporary wafer or panel carrier, and then two-side tap. The two-side tap is not the same with the tap that the thermal release layer tap, totally different. The tap is die-attached film. Okay, the thermal stably is better than the thermal release the tap, and then press the no good die, and it should be noted that the surface of the IC is toward the top. Okay, and then molding, epoxy, and the grounding. The grounding should be careful. Why? When we fill in the epoxy molding material at high temperature and cooling down to the temperature, the total wafer or panel will be warped. So when we backgrounding the EMC material, you can see that when at the edge, the chip at the edge will be ground larger than the center location. It means if we continue grounding and would like to approach the I/O of the central chip, the edge of the chip at the edge will be damaged. So this is why we want to induce construct the additional contact pad. It means we have tolerance to we will give the tolerance for the backgrounding. Okay. If we do not have the contact pad, actually this is just one approach. Use the contact pad. Another approach for other company for vacuum, use the vacuum technology directly reduce the warp from the viewpoint of the equipment. Another one is use the ring frame pressure at the edge to restrain the warpage. So different approach, but have a risk here, right? Because if we just use the metal ring directly restrain the warpage, maybe have some crack here during the process. So you also need to so depend on so this need to analyze, okay? And after the backgrounding, then RDO structure ball formulation and the dicing. Okay. So this slide just show you the die first, die down, and the die up. Okay. And it should be noted that here, at this moment, the die attach film is used here. Okay, is used here. And this slide I will like to skip because the die chip first, the die up RDO is fabricated by the same approach, the same film method. So I would like to skip this slide. And this slide just show you that why the fan out wafer level or panel level packaging become important, because the ATAL and the TSMC the requirement of the ATAL, for example, the iPhone smartphone, so many package structure within the iPhone structure now is used the fan-out packaging with the POP packaging on package structure. So this is why the requirement for such kind of the structure become increasing during the last 5 years. Okay. Now this is again just show you the panel level packaging or wafer level packaging become important. Okay. And actually, the fan-out packaging now become the key component in the iPhone smartphone. I just show you here an example in the iPhone 6 Plus here. This is the CPU for the iPhone 8/9 CPU. And we give a cross section here. The carton, the cross section, the figure is here. This is packaging and packaging structure. Okay. The yellow color, the substrate. Sorry. The upside by the packaging substrate for LPDDR4 is one structure. The bottom side A9 chip with the yellow with the green the color substrate is another packaging structure. So this is packaging the framework here, and the real cross sectional picture is shown here, and for this generation, the fan-out packaging do not use here because in the generation we still can see that they'll have two substrate here, right? 3-layer coalesce. Another one is 222 pick out the package substrate. But next the 222 build out the substrate will be replaced by the fan out the structure. Here, okay, conventional packaging and packaging for application process, the chipset. Okay, it should be noted that compared with the right side, the cross section, figure, you can see that the button, the substrate now is replaced by the RDL, and they do not have the smaller bond here, just directly have the RDL here. So in limited wafer bonding, solder reflow, flux, the cleaning, underfilling, and the packaging substrate, low profile here. So this figure is here. We have shown that I mark here is limited now. So by this way, the profile will be reduced and become thinner and thinner. Okay, this is iPhone 6, the top view here, and I just show you the TSMC, the fan out, the packaging. The TSMC fan out packaging code is an info packaging structure. I repeat again, the fan out packaging in TSMC, we have give it a name, info, and such kind of info, the structure have the packaging the framework here, just like this way. This is iPhone 7 or 7 Plus here, the cross-sectional view. You can see that this is AP, right? The AP now is the fan-out packaging because this is RDL and the solder ball. So the A10 AP is a fan-out package structure, and the memory side by side totally maybe have 4 or 8, about 4, right? Side by side, 1, 2, 3, 4. Actually side by side here, and this is memory is another packaging. The fan-out packaging with the AP stacking with the memories packaging. Okay. This is the true cross section for the packaging structure. you can find that the A10 AP die here, and the fan out RDL, 3 RDL here. Okay, the memory is at the top of the peak feature. So totally, the thickness reduced a lot. This is the OM picture, and give you a reference. Actually, the 3 RDL totally the thickness is about 50 micron, and the coldest the substrate for the memory is about 100 micron here. And you can see that the chip and the memory thickness is reduced about 165 micron and 105 micron. It means the chip have the based on grounding treatment. And as you know that original the wafer thickness is about 750 micron. So reduced now is reduced to such kind of thickness. Okay. Oh, this is the bottom side of the view for your reference. I will skip here. And the info, the technology, just I show you that this is the paper come from the TSMC in ECTC 2016 year. Okay. This slide just show you the case for electrical comparison. Actually, at the same size, 14 millimeter by 14 millimeter with the ball pitch 0.1 millimeter, and the 3D IC and the fan out and the info fan out and the other traditional 3D packaging. Okay. This is the important. This slide just show you the important packaging structure now for info POP structure, flip chip packaging structure, and the 3D IC package structure. 3D IC package structure is used in the CoWAS the memory cube now. And now I will introduce the fan out panel level packaging. Wafer and the panel just show you the size, right? If now the main strength is the 12-inch the wafer, and the panel size is always larger than this the wafer size. It means because the RDLs of the panel are fabricated by the PCB laser directly imaging technology, and the peak and the plate of die and the positive are by small surface mount technology equipment. And since the area of the panel is larger than the wafer, so more packaging can be met. Okay, and it should be noted that the wafer, the fan out panel level packaging, panel packaging is applied to low end and the low performance and the low pin count and the small device. Actually, the line width and the spacing for RDL is larger than 10 micrometer, but the number 10 micrometer is not correct now, because the packaging company and the foundry company just have working on how to reduce the width and the spacing for RDL. So actually, this number will be smaller than 10 micron now. And this slide just show you the example for the integration layout line for the panel level packaging. This is the slide. This is come from the IZN. The first is placement, accuracy, molding, lamination, laser driving, mechanical driving, and the laser printing, and the imaging and etch. Okay, so many equipment here, but the cost of the equipment compared with the foundry, wafer foundry, it's still cheap. It's still cheap, but actually for traditional packaging equipment, this the slide, this equipment is become expensive, right? But smaller than foundry equipment. Okay, this is the process for panel RDO by PCB and the laser direct image. Actually, from here, this is for die. For example, the die first face up the process, and actually, in the beginning, we will laminate the ABF. ABF is one kind of the polymer material. It's very important. And then laser driving and the copper seal layer and the photo resistant dry film lamination, and then we use the laser direct image and the dry film development to define the location and the geometry for the copper trace, and then printing, okay, and the dry film strip and the copper seed edge, and then repeat the process, previous process, and we can create another RDL, for example, RDL 2, and finally define the solder ball location and form the solder ball. And then this slide is very important. Actually, we have introduced the three kinds of the fan-out packaging process for high end, medium end, and the low end. The low end is RDO, first face down, and the medium end, for example, is is the RDO first at the face up. The high end is the RDO last and chip first and RDO first. Okay, by high end of the fan out process, the key technology is we will compare the RDO layer width and spacing. If the width spacing smaller and smaller, it means the technology is good than other company. So for high end, the RDO layer width and spacing is smaller than 2 micron. Actually now the width and spacing is almost 0.5 micron and 0.5 micron. Okay, and here I just show you the dual density process here. The dual density, couple dual density process is the origin come from the base side of the back end of the line of the foundry company. Okay, and the low end is come from the PCB equipment of the packaging company. Okay, so because of the limitation of the equipment, so the distribution layer width and spacing will be different. Okay. Okay, now I will introduce the chip first here. I will quickly again because we do not have time. Okay. Chip first, chip last. Chip last. Initially, we will introduce the caterpillar from the chip. Okay, and from the process, silicon wafer, a silicon panel. This is a temporary the silicon wafer or glass the panel. First step, we will fabricate the RDL and then press the non-good die with the caterpillar, okay, assembly. And then fit in under fill and the molding, okay. And after this process, we can dice in directly. Do not need to the metal reinforce here. It's okay. And this slide just show you the wafer bond process. In the previous slide, the caterpillar is below the C2 bond. Okay, C2 bond. Okay. Traditionally, the free chip bond is the C4 bond. Control collapse chip connection the bond. Okay. But for chip to bond, the gap between the chip and the substrate can be controlled. Okay, I will skip this slide for the demonstrating the placer, and this is the SEM picture for the demonstrating the chain, and this slide just show you we will remove the silicon wafer and create another side, and create the solder ball in the opposite the side, the surface. And actually, by the fan out packaging the process, we can embed the chip on the molding, from the wafer level system info packaging. Just as shown in this slide here. This is panel level the system in packaging. Okay, this is high throughput. Here I give you a summary and the recommendation for the talk, and I do not go through the detail, okay, because we have another speaker here, and just I told here, and this slide here, okay. Thank you for your listening. Thank you. Okay, have any question?
Thank you, Professor Lee.
Thank you so much, sir.
So we can, the participants having questions, please raise your hands. We will unmute your mic so that you can ask the questions. Participants, you can write in the chat box or raise your hands. Anyone?
Sorry, because today time is not enough. Actually, I can go through the more detail here.
No, no, Professor Lee, the PPT and the presentation was very practical, I would say. Very new things have come across. I hope the participants have also learned many new things today. It was very practical oriented. Actual moving towards the industry, how the work is done. You presented in a wonderful way.
Yeah.
I'm really thankful to you.
Yeah. If we have time, maybe next time I will introduce the CoWAS, yeah, chip on wafer on substrate, because the CoWoS the package structure is very popular and new for the NVIDIA and the TSMC. Yeah,
Okay.
because the CoWoS structure is focused on the interposer, the fabrication for 3D IC packaging for large area packaging. Applied to the high GPU and HPC. Yeah.
Right. So the participants are giving the feedback, very informative and amazingly explained everything. The one question is, how much cost for fabrication of one IC?
I
What is
just
they are
I just
asking the cost of fabrication.
actually the IC depends on your product, right? Yeah.
Yeah.
For example, if the IC have the very cheap IC for I need to say like that if the IC chip is applied to CPU or GPU, the IC is very expensive. I work in TSMC. Actually, one slot SLOP, one slot is the totally have 25 the wafer. The 25 wafer in the beginning need to more than 3 months finish one chip. Actually, if the 25 the wafer fail, sometimes earthquake, right? Earthquake. If the wafer crack, maybe need to several laser scar.
Okay.
So it's very expensive, right?
Very right. So thank you so much, I would say, sir, taking out your time and that too before moving to your vacation time.
Yes, thank you.
I really appreciate your time and the efforts you have put up. And
Yeah.
thank you, thank you so much.
Thank you.
We will
Thank you
be
again. Thank
connecting
you.
very soon for the further informative sessions from you.
Okay. Okay. No
Yeah.
problem. Yeah.
Okay. Thank
Okay.
you. Thank you so
Thank you.
much. Thank you.
Okay.
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 Ishika,
Bye-bye.
Ishika, you can take it forward. Okay.
We sincerely thank Professor Lee for sharing his expertise on semiconductor packaging. Your insights have provided us with a clearer understanding of the subject. We truly appreciate your time and knowledge, sir.
Okay.
Thank
Yeah.
you. Thank
you
you
so
Thank
once
much,
you.
again, sir.
Thank you.
Thank you.
Bye-bye.
Bye, sir. Bye.
Bye.
Bye. And now we can move towards the next session.
Our, our next session explores another crucial aspect of semiconductor manufacturing, etching processes under vacuum conditions. We are honored to welcome Dr. C. Ramachandra, consultant at ISRO and Director Semiconductor at 4C Bangalore. With over 40 years of experience, he has worked with ISRO, Tesla Semiconductor, CMTI, and Tech Semiconductor Singapore, specializing in VLSI circuit designing, MEMS, process integration, and semiconductor reliability studies. His expertise has significantly contributed to nanomicroelectrics, laser assisted technologies, and turnkey semiconductor projects. In this session, he will provide insights into etching under vacuum conditions, highlighting its role in achieving precision and efficiency in semiconductor fabrication. Without further ado, we invite Dr. C. Ramachandra to take the virtual stage. Sir, the stage is all yours.
Welcome, sir. So you are muted.
Good evening to all. Number screen perfectly. PPT.
PPT PPT go.
Am I audible to all?
Yeah, sir. You're audible and slides
Sir.
are also visible, sir.
Okay. Good evening. Today the topic is etching process under vacuum conditions. So I try to cover role of etching in device fabrication. That is the main theme here. And though etching can be done in vacuum condition, there are certain etching process which can be done in ambient condition also. I will just go through very quickly. And types of plasma etching system. When we say it is vacuum, it is mainly plasma driven etching. And I will go through few case studies which have been really done by us in a wafer fab, micron fab. I would like to impress upon you how interesting it is, how difficult it is, and how challenging it is to do etching process. Also, the another technique which is available is ion beam assisted etching. I will quickly go through that one and compare with that one plasma etching system. Also, because you are all academic institute actually, what you people can do. So there are hundreds of opportunities, but I will just mention one or two opportunities. It is not a limited, just to show you how you can contribute to the industry. Now, the whole etching process is important and relevant for device fabrication, device packaging and all. As a layman, you may not be knowing anything about device fabrication. The whole fabrication takes 2 to 3 months. There are more than 2,000 substeps in fabrication. That means if you start today, the final product will come after 2 or 3 months. It depends on the product you have chosen. Now, in these 2 to 3 months, what is happening to the wafer? As a layman, if you want to ask, there are only 3 things that happens. One is defining the space. We call patterning in a layman language. We are defining certain pattern. Then we are removing the material from some location. That is what we call etching. And we are depositing some material. It is called deposition. And all these things happens in a vacuum environment. That is why role of vacuum is very important in device fabrication. It is just like building a house. You want to construct a house, you have to define the space. Where has to be your bedroom? Where has to be your kitchen? Where has to be your dining hall? All these things you have to define. If you don't define, then you cannot plan it. Is it not? Then you are going to remove some material. Finally, you are going to add some material so that you get the house. This is the layman level of understanding. And these processes, they follow several times in some sequences. It is not that you do it once etching, it is the end. It is never an end. Etching happens several dozens of times. Deposition happens several dozens of times. Lithography takes place several dozens of times. So totally, the whole device fabrication takes 2 to 3 months, depending upon the device complexity, the specific device you have chosen. So this is your starting material, silicon wafer you have got. That means there is no device. This is the one actually. Now after 2 or 3 months, what you are getting after, when I say I fabricated the device, what is there in that device? As a layman, if you want to understand and if you want to see, this is the cross-section image of the device. There are so many layers, but we classify broadly them into 3 levels. The bottommost level, we call as a gate level. All the circuit element, active elements are present in this one. That means your diode, transistor, your capacitor, resistor, and the numbers are billions of transistors. This is the bottommost layer for any device. Next, middle one, we have a memory levels. We have various memories. For example, if you take a 512 MB DRAM, one chip contains 500 million memory cells like this in one chip. One chip dimension is hardly 10 mm by 10 mm. After that, we have contact levels, all we call contact loops. These are all metallization. The device can have 1 level metallization, 2 level, 10 level, 15 level. It depends on the device complexity. And much above that, we have got a passivation level, which is just for protection purpose, mechanical and environmental protection. It does not do any electrical function. So at the end of 2 or 3 months, these are the structures we are going to get from the silicon wafer. It is very important. For example, when I say memory level here, this should be present here only. This is a transistor, it should be present here only. If it displaces by even a submicron, it creates short or open. So that kind of accuracy, that kind of precision is required. If I want to fill some tungsten layer, before that, I need to etch it here actually. Here only I need to create a hole. Otherwise, it will not serve the purpose. That submicron precision is the main challenge in device fabrication. Now, the pattern definition process is called lithography together actually. That means we are defining the space in a device. How we do it actually? So this is basically we have a light source which passes through the mask actually, and we have an exposure system that get printed on the wafer. Of course, I'm just telling in a layman language, there are so many other processes, developing, exposing, all these things. So what wavelengths we choose, what steps, speed, there are so many process parameters. Basically, a photolithography system contains a illumination system, well focused, proper wavelength of the light that exposes the photoresist, and that pattern gets printed on that. Even in this photolithography, mainly there are two types of version. One is step and repeat, we call stepper. Another is step and scan. It's very, very complicated system. Don't think it is simple. One scanner cost more than $150 million. And a wafer fab requires at least 1 dozen of scanner to do the device fabrication, to meet that kind of quantity. So it is very complex system. But to understand in a layman language, the whole purpose is to create pattern, define certain space in the wafer. So that means if I use certain pattern mask in this one, and if I use proper photoresist and all, do the photolithography, what I am going to get on the wafer, I am defining certain space. Now certain structure is defined. If I use positive resist, I get like this. If I use negative resist, I get structure like this. The whole purpose of photolithography is to create pattern on the wafer. So first step is to create pattern. That means I am defining how my houses should be there, what should be here, what should be here, what should be there. So this is all planned as per the design actually. So this is in a very, very layman language I am telling you. It is impossible to go through any complexity of any of these processes. Once we define the pattern, the next step is to remove the material. So we have to dig out some material from certain pattern. So some of the important parameters, what is the etch rate, what is the selectivity, what should be the etch profile, and how do we stop that etch is completed. These are all the concerns we need to address. Though etch process looks easy, it is very, very challenging actually. For example, you see, I need to create a hole from here to here. The white one you are showing actually. Because after that, I need to fill some material. If I want to fill some material, I need to create a cavity. The size of the cavity, diameter is less than 0.2 micron. And the depth of the cavity is few micron. Challenge is very, very difficult because we are using certain chemicals, we are using certain gases. So deeper, the higher the aspect ratio, the probability that chemicals enters the deeper region is very less. So what is the probability it enters and etches? And even if it etches, it generates byproduct. What is the probability the byproduct will come out? If byproduct does not come out, etching will not happen. So entrance of the chemicals, which may be in the gaseous form, but to the bottommost of the structure, and removal of the byproduct, these are the quite challenging. So though it looks very simple structure, very, very difficult I will tell you. I just want to give an impression on how difficult this process are. So etching processes happens under two conditions. One is ambient, that means atmosphere. Another is vacuum condition. Today our main focus is on vacuum condition, but I will just quickly tell what are the important processes available in the ambient conditions. Now, if you want to etch some device or some structure in an ambient condition, the available technology are mechanical polishing. So it does not require vacuum. We can do wet chemical etching, it is a chemical process, and laser assisted etching, because most of the laser does not require vacuum. There are very few lasers which requires vacuum, but most of the laser work propagate in atmosphere. So these are the three important techniques, technology available for etching. Etching means removal of material in a controlled manner, in an ambient condition. But today our focus is not this one. We are trying to see it in the vacuum condition. So mechanical polishing, we can do it. It is a very poor selectivity. It does not distinguish whether it is silicon or silicon dioxide or aluminum. It simply removes it. So very poor selectivity. It is difficult to control thickness, because I want to remove 1 micron. I really don't know. There is 1.2 or 0.8. I do not know. Of course, it is a low cost. Any lab can set up, like a academic or R&D institute. Most of the time it is manual or semi-automatic operation, and it is non-localized. That means everywhere it removes. And one of the drawback is particle contamination, because it is a mechanical polishing, lot of particles will be entered. And in semiconductor industry, we spend millions and billions of dollars in controlling the particle contamination. That is the major killer of our yield. If at all your device fails, the first question, we see the particle contamination thought at every lab and every facility. This is the main killer. Therefore, we never recommend any process or any technology which generates particle contamination, no matter how good it is, how advantageous it is. Now, some improved version of mechanical polishing is chemical mechanical polishing. Here, we use certain chemical pads, chemically wet pads, that becomes more selective in removing some of the material. Some selectivity we introduce actually. So we can create very polished surface and uniform surface, and main thing, it is used for planarization of the surface. Why planarization is required? Many times when we do wafer level, we deposit BPSG, we deposit many layers. It won't be uniform actually. It will be curved. And if it is not uniform in thickness actually, next process like lithography becomes very challenging. So planarization is very important. For that, this is used. Of course, it uses chemical pads. It is not just mechanical polishing. It has certain selectivity with respect to oxide, metals, etc. Now, another process which is very popular in ambient condition is wet touch. Wet means chemical, wet chemical, liquid chemical. Again, it is a low cost, it has a very high selectivity, but poor profile control. So it is mainly isotropic. It etches in all the directions. And there are many safety concerns. We need to use fume exhaust, otherwise lot of health hazards will be there. So it is a cost wise, it is definitely big advantage. Selectivity is very big advantage. So these processes are mainly in the ambient conditions. Another process is laser assisted etching. It is localized. When I say localized, what does that mean? In the case of chemical etching, in the case of mechanical polishing, whole die is etched actually, whole substrate sample. But here I can go to any location of the sample and etch only that portion. That is why localized. So that localized advantage is not available in other options. But laser beam, I can focus on wherever I want. Only I can remove material and that localized. And the material is sensitive to the wavelength. That means I need to choose proper wavelength. For example, I want to choose silicon, I need to use one wavelength. I want to etch aluminum, I need to use different wavelength. So this is the one requirements or limitations. And process optimization is not easy. You may have a good laser, but unless you properly tune the parameter, the pulse width, the pulse repetition rate, laser power, the mode of the laser beam, so many parameters, you will not get good results. So process optimization is a bit tricky. Now our main focus is etching process under vacuum condition. That is what we are focusing on. So when we say under vacuum condition, what are the techniques available? So mainly there are two techniques available which requires vacuum. One is plasma assisted etch, another is ion beam assisted. So I will go through both of them with detail and compare what are the advantages, what are the challenges in this. So compared to the wet etch, that means chemical etch and plasma etch, if you compare, these are all the advantages. Directionality, when we use wet etch chemicals, it etches in all the directions. So most of the time I want to etch only in vertical direction in device fabrication. That is a requirement. That means I want to have 90 degree, but it is not possible in wet etch. It goes 45 degree. Whereas it is possible to control the direction to some extent at least in plasma etch by choosing proper parameters, process parameters. Selectivity, it is very high, but compared to this it is low. Compared to wet etch is not very high. So that is the bit limitation of plasma etch. Profile control, I cannot control the etch profile. It is isotropic, it etches in all the direction. But here, by tuning the process parameter, I can control the profile to the way I want it. And cost, it is definitely low. Any academic institute, any R&D lab can easily set up this facility. It is quite high compared to this one. Definitely 10 to 100 times more than this one. When we say selectivity, what does it mean? Suppose I have three different material. If I try to etch, if this material etches 10 micron, how much this material etches? It will be different. How much this? So this ratio we call selectivity. For example, this can be silicon, it can be aluminum, this can be silicon dioxide. They don't etch same rate actually. They get different etch. So that is defined by selectivity. Now, our focus is plasma etching. What is a plasma? You might be knowing it is a fourth state of matter. You take solid, if you heat, it becomes liquid. If you provide thermal energy further, it becomes vapor, it is gases. Now, question is what happens if you provide further thermal energy? That it gets ionized. Ions and electrons get separated because you have provided so much energy. That state is plasma. So it contains electrons, ions, neutral atoms. It is a mixture actually of this one. And in this state, it becomes very, very chemically reactive and it provides many advantages. So there are different configuration of generating the plasma. So we can use RF configuration, DC configuration. We can have high density plasma. So these are some typical process, if it is this one, what is the typical pressure we use it to require the generate the plasma? What is the operating power of the RF? We can use it. What is the frequency that is used? What is the typical flow rate of this one? What is the magnetic field generally we use to confine the plasma? What is the plasma density? And what is the electron temperature? Electron temperature means it looks 1 to 5 electron volt, 2 to 12 electron volt. But when you convert into degree centigrade, it is very, very high. 1 electron volt corresponds to about 12,000, more than 12,000 degrees centigrade. That means if I say electron temperature is 5 electron volt, it corresponds to 60,000 degrees centigrade. So that is why we cannot create plasma just by heating. If I want to create just by providing thermal energy, I have to provide a temperature of 60,000 degree. And if I provide 60,000 degree, whole building will melt and evaporate. We will not be there, including us. So it is impossible to generate a plasma by providing thermal energy. That is why we are using other methods such as RF, all these things, DC bias, all these things. So, but the temperature, the energy is very, very energetic. This electron volt corresponds to electron at the temperature of 60,000 degree. You can imagine what kind of chemical reaction it can take place. That is the energy we are giving to the ions and electrons. Ion bombardment energy. You see, these are all electron volt. 1 electron volt is something like 12,000 degree. If you convert it, it is probably we are in the sun. That much of temperature, a chemical reaction takes place. And fractional ionization and particle temperature. What is plasma etching? So basically, when we say plasma etching, plasma means it has a electron, it has a radicals, etc. Either the radicals or the electron has to react with the chemicals. And when it reacts, it generates certain radicals that is going to react with. Now, for example, CF4 itself may not react with silicon. But when CF4 reacts with electron, it generates fluorine radicals. This fluorine radical reacts with silicon, and this silicon, it generates a byproduct, silicon tetrafluoride. So that is why this is, we have to remove by volatile. This has to be volatile. That means the gas we are injecting, it should generate radicals that is chemically reactive. When that react with my material, that should generate a byproduct which is volatile and should be pumped out. If it is not volatile, it will again deposit on the substrate and create a lot of contamination of the problem. So these are the requirements before selecting this one. I cannot simply put certain chemicals. I must know the chemistry in the plasma condition. Plasma chemistry itself is very challenging and interesting. How the chemical behaves. Not only chemicals, how the radical behaves, how the free electron, free radicals interact. So we should have very good knowledge on the plasma chemistry. But basically, if I want to remove silicon, basically it should react with fluorine radicals. That fluorine radical comes because of the decomposition of CF4 by bombarding with electron in the plasma. This is a simple example. So typically, you have a plasma chamber, that is a vacuum system. You have two electrodes and gas is injected actually. And these gases are ionized. They have radicals, electrons and all. So electrode. So gas is injected from one end, gas is taken out from another end, and bias is applied. Whether it's DC bias or RF bias, it depends on the system configuration. Now, after the etching, we get different types of profile. It may be a kind of isotropic profile, maybe somewhat direction like that, or very vertical edge. So this profile, it depends on the process condition, process parameter, how we say. It is possible to tune my process for any one of them. Of course, getting pure vertical profile is difficult, but it is possible. But sometimes I need semi-directional edge, sometimes I want isotropic edge. It's all a matter of selecting the process parameter. In the case of wet etch, we always get isotropic edge. But in the case of plasma etch, I can get isotropic edge, I can get somewhat directional edge, or I can get perfect vertical edge, selecting and tuning and optimizing process parameter. Therefore, process parameter controlling becomes very challenging and very interesting to develop different profiles. These profiles depends on my process requirements. So what are all the typical plasma etch requirements? Selectivity. Suppose I want to etch silicon but not silicon dioxide, or I want to etch silicon but not aluminum, any adjacent material. Typically selection rate is more than 100. Typically requirement in industry. Etch rate, typically what we read is 0.1 to 1 micron per minute, because most of the time our etch thickness will be less than 5 micron. So even if I take 0.1 micron, it will take 50 minutes actually. It is not affordable. Industry production will affect actually if it takes very long time. Then non-uniformity. Throughout the wafer, you should etch uniformly. The non-uniformity acceptable in industry is typically 5%. And as I said, plasma system contains a lot of particles, ions, electrons, and some neutral particle also. There are probability, these are energetic particles. They can get entrapped in the wafer. So there should be limit. The number of particle, when I say contamination, it is particle, plasma particles. That should be less than this one. These are some broad guidelines. When I do device fabrication, because these particles get contaminated or impregnated in the device, there are possibility that it can create gate threshold. That should be less than 50 millivolts. It can create gate leakage current. That should be less than 0.1 nanometer. These are all the broad guidelines. And these guidelines will change from one family of device to another device. But we should keep these guidelines in my mind before developing the process. So there are different configuration of plasma system. RIE stands for reactive ion etching. RIE plus magnetic confinement. I can have a reactive etching configuration. I can increase the plasma density by applying magnetic field so that plasma get confined. Plasma density will increase. So this is also called high density plasma, HDP. Similarly, I can have RIE plus I can have inductively coupled plasma. I can confine the plasma by inductively coupled. Deep RIE. DRI means deep RIE. It is basically RIE, but we are developing certain process setup, new chemistry, so that it etches only in vertical direction and several very long profile it will etch. Microwave RIE. Generally, RIE uses RF power if it is dielectric, but here we use microwave power. It has certain advantages. The electron density, plasma density will be much higher compared to RIE. These are all some of the standard configuration used in the industry. This is typical RIE system. You have a chamber which is connected to the vacuum pumps actually. You have a controller, you have a process display. You can program the process and see what is progress in the process. As I said, the system configuration, it has an anode cathode assembly because either we have to apply DC power or we have to apply RF power. Then we have a vacuum chamber. Vacuum chamber should be supported by vacuum pumps. Typically, rotary and turbomolecular pump is good enough in most of the application. Gate valve to control the flow of the gases and mass flow controller. Generally, the reactor etching system, plasma etching system comes with 6 to 8 different gases we can connect, and we can control flow of individual gases. It's very important controlling the flow because that mixing ratio is very important. And to generate the plasma, either we apply DC or RF or microwave for generating the plasma. And one of the important parameters is impedance. Once we use RF or microwave, there will be reflection of the RF power. So that should be automatically minimized using impedance matching method. If that is not minimized, then lot of RF power get reflected and we never get the proper etching processes. Sometimes we use load lock so that the wafer will be in the vacuum for a long time. Another important point is endpoint monitoring. Suppose H silicon or H aluminum, how do I know I have to stop it? Therefore, many of the system comes with inline monitoring system. Once the aluminum etch is complete, it will give indication either it stops automatically or we can stop manually. That endpoint monitoring system is desirable in many cases. And answering the backside cooling. Some of the times we need to control temperature of the substrate. Therefore, there is a provision to cool. So these are all some of the important aspect of a system. Depends on your application. Some of them probably in some application you can eliminate or avoid backside cooling if it is not very critical. These are all the specific applications. So etch mechanism. In the case of chemical etching, it is purely chemical reaction takes place. But when we go to the plasma etching, there are two types of etch mechanism. One is physical sputtering because ions, there are energetic ions. If you say their energy, there are electron volts, and electron volts correspond to the more than the sun temperature, highly energetic. They come and bombard because there is a potential there. So it is a sputtering, it is a momentum transfer take place, it is a physical sputtering. So Jay, for example, we have seen sputtering. We use organ sputtering for thin film deposition. Similarly, here sputtering means it is purely mechanical transfer of the momentum. This itself we can use it for etching. The advantage is it is poor selectivity. So it does not matter whether it's aluminum or silicon dioxide, it keeps on bombarding and remaining. But the advantage is very high directionality. So another mechanism is chemical reaction. As you have seen, if there is a fluorine radical, it etches with silicon, generates SiF4, that is volatile, that gets exhausted, taken out. So it is highly selective, But chemical, because it is chemical reaction, it is isotropic. It is in all the directions. Sometimes we can combine both of them and get the desired profile what we want. I want, for me, isotropic is okay, then I can focus, I can set the process parameter that it encourages, it supports chemical etching and it discourages physical sputtering. I want only one directional, that means 90-degree profile. I develop a process where it supports mainly physical sputtering and discourages chemical etching. So it is a matter of selection, optimizing the process parameter. I can select any one of them and control the profile. That is possible in reactive ion etching or plasma etching. So there are library of chemicals already it has been identified. So these are all some of the gases which are used actually, main etchant spaces, what material it removes. So we can etch silicon, we can etch silicon dioxide, silicon nitride, then we can etch aluminum, so many metals, oxides, semiconductor. The library is there. Today it is well established, but there is always scope for identifying new chemical, new species, which provides better performance. It is always an open area. As I said, creating this kind of vertical profile is very, very difficult actually. Though it looks easy actually, it is very challenging actually. And sometimes this whole diameter is less than 0.2 micron and the depth is couple of microns. Now, there are two challenges because we are putting chemicals here which are gaseous. What is the probability that these chemicals enter into this deep hole? Otherwise, it will not react at all and remove. And after reacting, what is the probability this byproduct will comes out and goes out of the chamber? These two things should happen. That is why creating this kind of vertical holes, high aspect ratio holes, quite challenging, and it requires tuning of process parameter very accurately, very precisely. These are all the steps involved in plasma etching. So basically, we put gases through mass flow controller, very well controlled flow of the gas. These gases generates radical in plasma by bombardment electron impact and dissociate the gas molecules. And these diffuse through mode of transport and get absorbed by the surface. And after that, they will undergo chemical reactions. And the byproducts has to be released from the surface. That is very important. If these byproducts remain on the surface, it is of no use. And they should diffuse and go back to this gas phase. And from there, it should get exhausted. So it is very important selection of the proper precursors. That is why how good it is in ionizing and creating the precursors, radicals, and how effectively it moves into the surface of the substrate. That is why the wafer size, the point of injection of the gas, how much distance it has to be kept, and where is the point of your vacuum sucking point. Gases should not be injected very close to the point of sucking, vent point. Otherwise, what happens? You are injecting the chemicals, it directly goes to the vacuum pump. It never reacts with the substrate. It is of no use. Therefore, point of injection of the gas and point of vent to the vacuum, they should be diagonally opposite and therefore should be somewhere in between. So there are so many design aspects actually. I'm just giving an idea. So this is how it says you are introducing the species into the chamber actually. They get radicals and they must move to the substrate. That is very important. These radicals, if it goes to the vacuum chamber, it is of no use without reacting. Therefore, transport of to the surface. And not only surface, they should get absorption. Otherwise, if it simply comes to the sample and goes, does not doing any purpose. It should get absorbed actually. And once it gets absorbed, it has to generate the chemical reaction. And the byproduct is very important. They should be dissolved. If byproduct remains here, it is a very, very severe problem. It becomes a contamination. Then we are ending up with more problem than solving this one. Therefore, for selecting the proper recipe, for selecting the proper chemical precursor, we need to consider all these criteria. What is the probability? How fast it transports actually in different direction? How it gets absorbed to the surface? How it effectively reacts? how the byproduct get dissolved and go to the chamber. Everything should happen actually. When one step misses, then we are adding more problem rather than etching. Now, suppose I want to etch aluminum or I want to etch silicon, say maybe 1 micron or 2 micron. How do I know it has etched 1 micron? Otherwise, I will be unnecessarily overdoing if I limit. So there are many inbuilt monitoring tools. So there are so many. Some of the equipment comes with this monitoring tool. If suppose I want to etch 1 micron, it gives a signal all alarm etching is completed. They are based on the spectroscopic or optical reflection, etc. They have got their own advantages and limitations, but it is the option. If you want to buy plasma etching system, you can buy monitoring tool also. It is not a embedded in all the systems, but you need to demand, I want endpoint detection. Also, this endpoint detection, it serves for certain materials. Suppose you have endpoint detection for aluminum, you may not use it for other materials. It is well tuned for that one. So for silicon dioxide, you may have to have another. So these are limited, but if you want specific application, you need to buy and get tuned for that. So as I said, etch mechanism. So there are two: chemical reaction and sputtering. Chemical reaction takes place in all the directions. Sputtering takes place in vertical. So using proper parameters, process parameter, I can encourage one of them or I can encourage both of them, and that way I can get desired profile. So the process rate is very important. Etch rate, it should not be too slow. I cannot take hours together or days together. At the same time, it should not be too fast. If it is too fast, everything happens in few seconds. It becomes very difficult to control. Selectivity is very important. I'm etching silicon, but I don't want to etch aluminum, or I'm etching aluminum, I don't want to etch silicon dioxide. So we need a selectivity generally more than 100 in industry. Etch profile, some application isotropic is okay, some application directional etch is okay, some etch application I need vertical profile. That is quite challenging. And particle contamination, it should be limited. Otherwise, ultimately, it degrades the device performance. So the important parameters, how we can tune it is, one is the power, whether it's RF power or microwave power, it affects the process. And distance between anode and cathode, or electrodes, we can say simply. Gas flow rate, to what extent you are pumping the gas. Is it 50 SCCM, 10 SCCM, 20? These are the things which affects. Impedance mismatch. It is very important when you use RF or micro power. Impedance mismatch should be less than 10%. Otherwise, lot of power will be wasted at the electrode. It creates more unwanted results. In some application, we use separate temperature to improve the performance of the chemical reaction. These are all not something fixed actually. We need to identify our particular process, what temperature is ideal or suitable. Etch rate means it is the number of how many micron it is removed per minute. As I said, too high etch rate becomes difficult. Too low means it is not compatible for manufacturing. I cannot take hours together to etch. So types of system, either I can work with a DC plasma. This is okay as long as my sample is conductive. Otherwise, I have to go for insulating sample, RF plasma. I can have a plasma with inductively coupled configuration. I can use microwave. So each one of them has got their own advantage and drawback. The main parameter is what is the electron density, what is the ion density, what is the electron temperature, ion temperature. These are all different in different configurations. That way we can use it for our specific applications. So this is typically, you can see this system. You have two electrodes and you are biasing either DC or RF or this one. You are injecting the gas actually, plasma is generated, sample is kept here, then gas outside is here. It is important the gas inlet and gas outlet that is going to the vacuum pump should be diametrically opposite. Suppose you are injecting the gas here, you could put the vent here only, vacuum pump. Then these species will just simply go to the vacuum pump. They never react with the sample. That is why positioning of this gas inlet and gas outlet is very important. As I said, sputter etching. If you want to use only ion and you don't want chemical etching, then you can get a vertical profile like this. Because it is basically sputtering, your mechanical bombarding. There is no chemical reaction. When there is no chemical reaction, you get vertical etch. You can get it. So basically, it is reaction. The electron or ion interacts with the gas which I am injecting. These gas radicals themselves are not reactive, but when they are dissociated, like CF3 and 4, they become chemically reactive, and my substrate material reacts with these radicals and generate a product which is volatile and pumped out from the system. So H rate is important. H non-uniformity, typically my requirement is 5%, not more than that one. Chemicals and precursors, it depends on what materials I'm going to use. There is today we have a library of different precursors, and there is a scope for developing new precursors, which provides better performance. It's always welcome. Suppose today I am using CF4 for etching silicon. You can find some other chemicals, precursors, which gives better results in terms of the H rate, in terms of the particle contamination, all these things. There is a scope. This is a unlimited. And endpoint detection is important in some, particularly in manufacturing environment, and process optimization for different materials. We need to develop the process and optimize it. These are all the common gases we use it actually. We use SF6, CF4, then NF3, C2F6. All these things are chlorine, HPR. There are libraries. There is a vast library. It is available. And for etching this kind of things, we go for preferably ion milling types, or there are some patented process which we call Bosch process. And today we are able to generate holes which are high aspect ratio. This diameter is less than 0.2 micron. It is 2 micron. We are successful in etching this kind of structures. Plasma monitoring tool, there are several. Many new things can be added up. These are all optical reflection, certain spectroscopy based activity. Now, having said this one, I'm going to discuss two case studies, two important projects which we did in Micron Wafer Fab in Singapore. I'll tell you what was the problem, what is the challenge, how we solved actually. So one is detection of IBC, another is detection of cell-to-cell short. What is IBC? IBC stands for insufficient buried contact. It is whenever a device has an insufficient buried contact, it provides certain unique failure signature. That means we realize only at the end, and it is very difficult to confirm. Another problem is we can only suspect. Unless we confirm what kind of corrective action takes place. In industry, confirming the root cause for failure is very, very important. Every 6 hours delay in finding the cause cost $1 million. That means if we take 1 day to find the cause, already we lost $4 million. Imagine if we take 4 days, it is $24 million. The R&D lab can be set up in India. Is it not? That much money we are losing. So time is the very, very important. How quickly we do it. So that is important. I will explain what is IBC and how we developed the process to catch that one. It was done almost, I can say, we are the first in the world to develop this technology at that time, 1990. To understand IBC, so you need to understand polyplug. Polyplug provides electrical contact for many of the functional blocks in devices. It provides structural support for many of the functional blocks like memory cells and all. It is a very electrical contact it provides. It provides structural support, and we have to make sure that this polyplug get impregnated in the silicon substrate to establish a good contact. If you take this one actually, for example, all this bottom you have polyplex. You see the whole tungsten silicide contact is sitting on the polyplex. These are all the memory cells sitting on the polyplex. All elements are sitting on the polyplex. This polyplex is connected to the silicon substrate. So there are billions of polyplex like that in a device. When I say a DRAM of 512 MB, what does it mean? There are memory cells of 512 million memory cells in one chip, which is few millimeter by few millimeter. Each one of them is sitting on a polyplex. That polyplex is connected to the substrate. That is makes electrical contact. In addition to that, there are tungsten contact which is sitting on the polyplug. So polyplug is one of the important structure in device fabrication. When we fabricate the polyplug, actually, this is silicon substrate, this is polyplug. We should get impregnated into the silicon substrate by few nanometers. Otherwise, it does not provide good electrical contact. So when it gets impregnated, it provides a good contact. When you go to the next slide, it is just making contact. It gives marginal contact. Device may work or may not work when polyplugs are just sitting on the substrate. And sometimes it is not even sitting, making loose contact. So high chance it does not work. So this we will not know until we completely fabricate the device. It's very difficult to monitor these things because what we are talking is 1 or 2 nanometer this impregnation. And once we completely fabricate the device, we do testing. There are millions and millions of memory cells are there. Some of them may not work actually. And the root cause might be improper contact of the polyplug. But how do we get from here? Now from here, if I want to go and see this polyplug contact is good or not, and confirm this failure is due to the polyplug, and tell to the fab, it is very, very challenging because silicon, substrate is silicon, polyplug is silicon, this memory cell is silicon, and there are plates above that, there is silicon plates are there. There are so many silicon. So when I am trying to remove this and reach the polyplug, even substrate may get damaged actually. So controlled removal of this polyplug, all these so many other layers is very, very challenging, and we were successful in developing. For example, if you consider a memory cell, the oxide wall thickness is less than 0.2 micron, the cell height is 3 micron, selectivity, the minimum required is 30, but desirable is more than 100. That means I need to etch the polysilicon without damaging the other structures actually. So these are all the requirements. And we didn't have a luxury, we didn't have a system with ICP or ECR because they are quite expensive and maintenance cost. And we did not have any special chemical like this, which have very high selectivity, but they are hazardous actually. With a limited resource, we have to do it actually. And we have developed this technology for the first time. And this was the approach we have chosen: retain the oxide wall, controlled removal of tungsten silicide, controlled etching of the cell plate, etch memory cell, DRAM memory cell, controlled etching of the polyplug, and retain the impression. What we have to see whether impression is good or not. For example, you take a small banana plant in the agricultural plant, you lift it actually, you can see how deep it has gone, the impression. So if impression is good, that means it's deep, the plant is good actually. It will grow and give the yield. If it is loosely connected, it may not get soil, it may not get fertilizer, it may not get water. So it is just a matter of the time, few days or few months, it will die. So same logic here actually. If impression is good, that device is good. If impression is poor, likely, they're very likely fail. And our failure signature should match with the impression. That is the challenge we have actually. So these are the important process parameter we optimized to develop this process. See, we have a silicon substrate. This is silicon. We have a polyplug, which is also silicon. This is a memory cell where the data, DRAM memory is saved. That cell is silicon. And over that, there is a silicon plate. See, we have to use so many silicon, but at the same time, I should not damage this substrate area. I need to retain the imprint of this polyplate. That is a challenging. So we have developed the process and we were successful. See, after removing all these things, this is what we call moat. And this is the imprint what you are seeing. So when you remove it successfully, every layer, if this imprint is there, that is means my polyplug had a good contact. So if it is not there, there is a failure. And we have taken some failed device. We have seen very exactly which location it has failed, and we have done similar process. Now you see the imprint is missing compared to this is a good location, good location. Here see imprint. So this is a failed bit, and here imprint is weak. So this was the technology we have developed. Before that, we were using very complicated and expensive technology. That is focused ion beam. That is very, very slow process, very expensive equipment, and at a time it can be used for one location. But here, throughout my chip, I can go to etch everything. There can be multiple IBC. I can define, I can identify easily in one step. This was very, very cost-effective technology we developed actually. And those days, you were not permitted to apply patent. That is the industry. Industry don't want other competitors to know what we have. They don't encourage publication. They don't encourage patent. Of course, after 12 years, they permitted me to publish. Now it got published actually. I'm just telling this story how difficult it is to work in industry and develop this kind of technology. So another project I have taken is in memory cell, there is a short sometime between the two cells that creates problem. Again, if I say there are 512 MB DRAM, there are 500 millions of cells in one die. The die size is less than 10 by 10 mm. So there can be short at any point actually. How do we identify this kind of short? So as I said, this is the finished wafer actually. If there is a short, we come to know only after testing. And there are so many layers. If I want to access these memory cells, I need to remove all this layer. So I should not damage these cells. And the spacing between these cells in some cases is 0.2 micron. I should see is there any short at this stage between these. Very challenging, and we accepted and we developed actually. Again, this is the structure of the cell. This is a polyplate. Again, this is a polyplug actually. The cells actually. This is a polyplug. This is silicon substrate, and in between oxide. So it is a controlled removal of these layers without damaging any of this cell area and identify defect. The spacing between this is typically 0.2 to 0.3 micron. And if these structures are present, we put it in SEM, we cannot see anything actually. So how controlled way we are going to etch it, these layers, that was the project we have taken. And we have successfully developed this technology in 99 in micron wafer. So you can see polyplate. This is cell location. Unless we remove the polyplate, we cannot see the, for example, this is one. When polyplate is there, if you put it in SEM, you cannot see what is in the bottom happening. It creates shadow. So we need to remove it actually. We have done in a very controlled way without damaging this one. So this is the cell dynamic memory DRAM. When you say DRAM, when you say cell, where the data is stored, you only program it 0, 1, where that data is stored. Each one, what you are seeing is the location where the data is stored. These are all the memory cells. So you are successful in exposing the memory cell for the first time. Nobody has done it, but you are not allowed to patent. That is a different story. It is an industry business. That is different. But we have done it, and we were very happy to see the memory cell. This is only a small part I am seeing. Throughout the wafer, there are 512 million this kind of cells throughout the wafer. Now we have taken a failed sample where we had a signature which is suspected to be memory cell-to-cell short, and we did same process, and we did the process, and we identified. You can see short between cell-to-cell after etching, so we could confirm. So this technology, both detection of IBC and detection of cell-to-cell short, was very, very wonderful experiment and project for us. We were successful. Those days, these are all the work done in 99. Okay. These are all the plasma-assisted beam system. Now, when you come to the plasma-supported system, there is a sample, the wafer, which can be 8 in diameter, 12 in diameter, or it can be dye, which is 3 millimeter. When I put this sample in this chamber, whole area get exposed in the plasma etching. That means etching happens everywhere. It does not see because it completely exposed actually. In some application, I want to remove the material. I want to etch the material only on some selected part of the die. Selected part. I don't want to etch completely. Suppose there is a silicon, there is aluminum, there is a tungsten. I want to remove in certain specified location, something like few micron, 1 micron or submicron, but not throughout the die, not throughout the wafer. Is it possible? The answer is possible. This kind of etching is possible, but it is not by plasma etching. It is another system we call ion beam assisted etching. So here we can etch any location you define, submicron feature. I can remove the material. So it's a very, very complex system, very expensive system, not less than 10 crore rupees. It is very slow process. That means throughput. So it cannot be used for manufacturing in event. So it is for some specific purpose and it requires a lot of skill in the job. It is not easy. A person should be well trained and well thoroughly professional. It is highly localized. I can remove, I can etch the material, you define the geometry. At that within a micron accuracy, I can remove. I don't need to remove the, I don't need to etch the complete 8-inch wafer, 12-inch wafer. You define geometry to the micron accuracy. It is mainly used for fault detection and confirmation. It is not used for production purpose because such a low throughput industry will collapse if you do etching. But some industry, after you design, after you fabricate the device, we come to know that device does not work. Because we do design, we don't know whether chip is working or not. After fabrication only we know. But then what to do? We need to identify the fault, design fault. To identify the design fault, and not only that, we have to correct the design fault. That means, okay, I find some metal link is missing, or some metal link is extra, I need to cut it, I need to remove it. So I do this one, again I test the device. And if it is working, that is the confirmation feedback to the design people. You see, look into this. This is the mistake happened in the design. You correct this mistake, your chip will work. So this is called VLSI circuit-aided technology, and here ion beam assisted etching, it is highly localized compared to the plasma etching. Both does etching, but plasma etching etches complete sample wafer, whether it is millimeter or inches or the 8-inch or 12-inch. It's global, it is a global, whereas it is highly localized. When I say highly localized, it is submicron accuracy, and it is mainly used in fault detection and confirmation, and I feed back to the design people what mistake has gone place so that they can correct it. And whole things happens in few hours. So designer get a feedback within few hours. So the system contains ion source because it is ion beam assisted etching, ion column because these ions has to be focused well with proper lenses. It requires high vacuum, something like 10 to the power of -7 torque. We need detector, and there are many gas delivery systems. We use, again, just like plasma etching system, we use different gases. Here also we use different gases for different sample. And stage is very important. Precise movement of the stage is very important because I need to do etching in a particular location. That precision should be submicron. So it is a laser guided stage. It is not a conventional type. So I can go to that location with the precision of submicron. That is the advantage. It's a laser guided stage. And process control. We have to optimize various processes. So this is a typical system. You have a process module where you load the sample in the wafer. Then you have a ion gun. There are so many lenses are there. Ions are focused and it is made to scan actually. And there are so many control in it actually to optimize the process. To look at it in a way, it is called a focused ion beam system. There is a system, the focused ion beam is generated inside the vacuum actually, and it is a IR microscope to monitor this one actually. GAE means gas assisted etching. It is again a kind of chemical etching. It is also plasma etching because we are using gases in a plasma stage for etching. And We have a navigation tool because we have a design data. We have a design layout that provides which location I need to do certain surgery or certain etching. That data is fed actually, and we have a laser guided stage which will move the sample to that particular location where beam is coming. That means it is submicron accuracy. So we cannot manually move it and go there. These are all fully controlled. These are the important assemblies of the whole system. You must have a navigation GDS from the system designer. We have to focus on beam system in ultra vacuum. Various chemicals we use it that enters and get into the plasma state form that chemically reacts. Either it can be used for etching or it can be used for even deposition. Very localized. Then the whole stage movement is by laser driven, laser guided. The accuracy is submicron. We can position the sample, we can position the beam with the submicron accuracy. So this is called microsurgery. That means you are getting the ion beam well focused on a device. The device is positioned exactly location where I need to do surgery, and I am injecting the chemicals, gas assisted H chemicals. I can control the temperature, I can control the flow rate actually. The stage is driven by laser assisted, laser driven this one, and night software is there that if you feed GDS data from the designer and whatever the location you choose, at that location stage will go, sample will just brought into that location. So these are all the important features or configuration of this system. So if you want to buy, it is not just a focus on the system. You need to make sure that system has a laser guided stage movement. It has a CAD navigation through night software. It has a gas assisted etch. Without this, you cannot do etch. So if you simply have a focus ion beam, you cannot do. It must be supported by gas assisted etch assembly. There are different nozzles, quad, tri nozzles, different gases will come, and IR microscope or online inspection. And we can do both front side and back side etching capabilities. This is a ion source actually, a gallium liquid metal ion source actually. So it is at the top of the system actually. The liquid gallium is filled in here actually. It gets extracted by this capillary and ionized and impinged, accelerated towards the sample. So it has many advantages. It has a vacuum compatibility. It is wettable with tungsten. It has a low melting point and high boiling point because it should melt and evaporate. The melting point is around 30-35 degrees or so. And it has adequate surface tension. And main thing is chemical compatibility. It does not react with sample. That is important. Samples of our interest. And proxy to silicon in the periodic table. That is also advantageous because we can see gallium and silicon actually. They are somewhat close. So lot of momentum transfer happens easily when they are very close to this one. So we can use this ion beam itself for imaging, or some system they come with electron beam also along with ion beam. We can use electron beam. That means you have an ion plus electron microscope. So if you use electron beam, you can use electron beam for imaging. If you don't have also only ion beam, you can use ion beam for imaging actually. But the contrast will be different. If you use electron beam, you get secondary electron image. When you use ion image, the contrast will be slightly, but it does not matter for our applications. So typically the sample we are using is few millimeter. And sometimes we may not have any reference. That means we don't know where exactly to go. I need to do this etching in certain location with submicron accuracy. How do we go to that point? Particularly when there is no reference point. Therefore, the precise positioning is possible only when you have navigation assisted by laser driven stage and CAD navigation data. So when we decap the sample and put this one, for example, we get lot of metal patterns. If you have some reference, for example, from this bond pad, how many micron you have to move, then you can go to do the surgery. That means you can do etching. But sometimes this pattern is also not visible. For example, you go to copper devices, you don't see any pattern. Then I want to do some surgery here. How to go? Suppose these are all thousands of microns from here to here. Even if I miss by 2-3 microns, I'll be doing the deposition or etching in some other location. So my whole purpose will be defeated. That is why in this kind of cases, or when there is no reference points actually, it's very important, it must to use navigation tools supported by laser guided stage and night software. Typically, ion beam energy, either we use 30 kiloelectron volt or 50 kiloelectron volt. There are various process parameters we need to optimize, otherwise we don't get the proper results. Pixel size is very important, pixel spacing, dwell time, refresh time, the nozzle spacing, how closely you keep the nozzle through which chemical comes and inject to get into the plasma state, nozzle temperature, temperature gradient, all this plays very critical role in optimizing the process. So this is the people, design people give. If it is a 3 level, they give the layout. Sometimes they have 5 level, they give the design layout. From this one, this data you must see where exactly you have to come. That distance you have to measure, that should map to the device. This is the layout design. Now, suppose you want to do etching somewhere here, you want to remove some portion here, metallic portion here. How do we reach this position? So this data has to be fed to the system. The system should move the stage and get into this location. So what we do actually, we have to decap the sample, because normally what we get is a packaged ICs. A packaged IC I cannot do. I must remove the packaging material. Now the whole die is set. Now my etching should be anywhere on this die. My die size is 10 mm by 10 mm, 5 mm by 5 mm, 20 mm by 20 mm. I may have to do at any one particular location with micron accuracy. So how do I move the beam to exact location? That is important. But before that, before doing this, I must make sure that all these wire bonds are intact. Because after doing this plasma etching or ion beam etching, I am going to see the change in the performance. Now device is not working. I want to make this device to work by correcting the mistake. Therefore, for checking that one, these wire bonds should be intact. It is very important to retain the wire bond throughout the process. Now, this is an example where I need to etch. That means I need to remove the metal too. Metal to me, there is already one metal level in the top. I have to go to second metal level. This was the project. We did it for Wipro. In fact, first project we took it actually. Of course, they provide all the data, all the GDS layout, everything they provide, and it is all under the confidential agreement. You have to sign NDA. All these are procedures actually. This is the particular location where the metal 2 is here actually, and they want to disconnect because it was noticed that this was wrongly connected, and if we disconnect this one, my device is going to work. That is the analysis done. The device was not working in the first design. After careful analysis, after studying the GDS, this was wrongly connected. It should have been avoided. That was a mistake. But how do we know it works? So here we etch this metal. This is micron, few micron only we etch. Then we do testing. Because we do testing, it is important to keep the wire bond integrity. Wire bond should never get damaged in the whole process. So then we reach the metal desired location. We reach this location by GDS data. Then we use ion beam to etch the material. See, the aluminum is etched here. Very, so no, just hardly 1 micron. So now this is disconnected. After that, we tested the device and it is found to be good. So this is a ion beam assisted etching. That means I can go to it. Now I'm not etching the whole wafer, not etching the whole die. I am going to the submicron location. I'm etching 1 or 2 micron or 0.5 micron. Similarly, it is not only etching, this can be used for even deposition. Suppose I want to deposit somewhere, some metal is missing, connection is missing, device is not working, and we come to know after device is fabricated. So what we do it actually, we take the device, see we deposited the material. Here connection was missing from here to here, we deposited, and after deposition, we test it again. Because we have to test it, we have to maintain the integrity. Then if it works, that is the feedback. All these things happen in less than half day. You believe it or not. You bring the sample failed device after design, and we analyze, we try to identify which are all the faults from the design. Then we take the sample, we test it, and we do the either etching or deposition. Again, we test the device and give feedback to the customer. I have served more than 200 customers in India. I was director and I was the first person who set up this VLSI circuit technology in India, and we have served more than 200 customers. Also, we have served many USA companies and all. We can create, see, we can etch very good wire. Suppose you have some metal layer here, top metal. You want to do some surgery at the bottom, you can create at this location and do some further etching or deposition next level. Like that, we can go to another level. This is various wire structures we have created actually. So what is the summaries actually? Any precise location, you have to identify using laser assisted or guided stage. It is very difficult if you don't have laser assisted, because manually if you want to do, there will be a lot of error. You want to etch it some location. For example, I have shown this figure. You want to etch it here, but if you go to some other location, you may having same pattern. You understand that is the pattern, that is the metal you want to cut, but that is not the one. So you must go to exact location. So with the submicron accuracy, that is a challenge actually, and that requires laser assisted guidance. Without that, CAD assisted navigation, we need to have the data, GDS data from the customer that should be fed to the CAD tool in the system. And either we can do etching or milling or deposition in submicron feature. We can deposit metal, we can deposit insulating films. And this is basically this is very popular word is microsurgery. It is also called VLSI circuit technology, and we can create a lot of 3D structures. Today, it is becoming very important. When we go to the nanotechnology, we need to create a lot of 3D structures which serve as a very good sensor or very good coupling unit or very good, application, nano sensor, nano structures, all these things we can create using this technology. Of course, you can find a lot of literature, papers and all, but I have written one book on this VLSI circuit technology done by 2016 or so, and this is the only book available in this area. As far as textbook, paper you get thousands, no problem. If you have time, sometimes you can refer. Just for knowledge sharing, I have written long back. Now, when you have seen, you people are always academic institute. Academic institute, I have gone to many times. At the end, they ask, sir, what we can do at the academic level? Of course, money is the criteria. You cannot think of investing crores of rupees in a system. Your management will not agree. So you cannot think of that one. But management definitely supports if you propose a project which is of few lakhs rupees. There are hundreds of research projects where you can you can contribute very good to the industry by solving the problem. There are hundreds of problems. I just want to tell one or two just to make it this one. There are few R&D opportunities. Whatever the example I am giving, it is not limited. There are hundreds, but generally whenever talking with academic institutes, R&D institutes, I say look into this problem. The main problem with academic institute is that you do not know the problem. You do not know what industry is facing the problem. When you do not know the problem, how you can solve it? Therefore, you need to know what problems are faced by industry. Then you can try to think of some solution. And you will not know unless you go there, you interact with them, you see how the process runs, what are the challenges. So this is a big gap today. So I'm not trying to cover everything. Just to complete this one, I'm giving one or two examples so that you can start thinking in what way you can contribute. So one of the challenges we are having even today is process for etching the copper. Earlier, during 90, if you look into the research paper, copper was used actually. At least you can see, if you see research papers, most of the research was on copper etching, many papers, copper deposition, copper etching. But we have faced a lot of problem, device problem because of the copper, and copper was boycotted from semiconductors. It is such a severe problem we ended up. But today, unfortunately, we have again welcomed. There is no real friends or enemies. Sometimes copper was enemy for semiconductor industry. Today it is one of the best friends, because without copper we cannot move on. So what I'm telling you, It depends on the situation, it depends on the time, it depends on the device structure. Once upon a time, copper has created a lot of problem, hell of problem. We suffered a lot. Our yield was reduced mainly because of copper. We stopped and went to aluminum. We get rid of the problem. Today, technology has shrunken. Again, we have come to copper. But etching copper is very, very tough and challenging even today. We don't have a proper technology. So this is one problem, where you can think of how to etch copper. The process should be acceptable to industry. It should be industry-friendly precursors you have to choose. It must have a proper volatile byproducts so that it does not create contamination. Another thing is endpoint detection. It may not require a lot of investment. Academic institute can probably focus, and definitely I'm sure you can sell the tech to spend even 5 lakhs, you can sell the technology for 50 lakhs easily if you are successful. Industry doesn't mind spending 50 lakhs, 1 crore if you know that, if you develop. So these are all technological challenges we can focus. I'm just giving 1 or 2 examples. So in ion beam etching, one of the important consumable is gallium liquid metal ion source. In this system, the problem is we cannot switch off the ion beam because again we want to turn on. It is very difficult. Lot of processes are there, so it is kept continuously. Whether you use it or not, system will be on, and it gets consumed in typically 1 month. If you use it, it does not matter whether you are using the system or not. Therefore, you must plan using the equipment for 24 hours. Otherwise, you are ending up with burning the liquid metal ion source. And each liquid metal ion source, lifetime is 1 month. It costs nearly $1,500 if you want to buy new one actually. That means every month I have to spend. It's very difficult. Even manufacturing industry, we feel the heat. And academic institute, they will say, better you close down. If you every month you go with a bill of $1,500. But there are some technology for refilling this one. It is a liquid. How you can inject this liquid in this capillary tube? This is a technology you have to, academic institute can try to do it. Why I'm telling is, in Pittsburgh University, one professor is doing. He's really doing and he is earning money. If some professor is doing in Pittsburgh University, why can't you do it? Why can't you try? So you can buy this 1 or 2 units and gallium is available. See how gallium can be promptly injected in this capillary. This is a challenge. It will save a lot of money and big contribution to this. So if you, what we understand from the Pittsburgh University, the cost of refilling is less than $200, but they are charging $600. Still, it works out much cheaper than that one. Therefore, if you can find a way of refilling the gallium with a cost less than $300, and you charge money to the industry under $300, you are earning money. So, because every month you have to change one system, one ion beam, it will save a lot of money to the user, and this is a problem. Academic institute can focus because it does not require big investment. So another, it is not directly related to the etching, but etching monitoring. Many times we use electron microscope, we use transmission electron microscope, we use focused ion beam microscope to see the profile. And all these microscope, they use a lot of apertures. This aperture should be of proper size and particular material, vacuum compatible material like molybdenum, etc. Today we are importing magnification calibration standard and apertures we are importing. So don't we have technology to make a hole of say 5 micron circular hole? Don't we have technology? Do we need to import it? Because this aperture goes bad after some time, after 3 months, 4 months. I need to put another. Can you take a strip of aperture and drill a hole of say 5 micron, 1 micron, whatever they do there, circular hole? Do we need to import or can we make it? Can academic institute start developing this technology? Similarly, magnification calibration standard. One standard cost more than $10,000. Some reliable standard I need it to check that my magnification is correct. Can we make some reliable calibration standard so that I can use it in all the microscopy, optical microscope, electron microscope, etc. This will save a lot of money to the industry and to the country. I'm just giving one of the examples. It does not mean you have to focus only on it. I have more than hundreds of these kinds of examples. This is, I'm just trying to think you how you can work and contribute to the industry. This is my essence of the presentation. I thank you for the North Camp University for providing the opportunity. I'm very glad to interact with faculty, students, and research team. You can always contact me if any support is required. Now I'm happy to answer if there are any specific questions.
Thank you so much, sir. I request all the participants, if any queries, please raise your hands or write in the chat box. Any queries you can write in the chat box. Ramakrishnan. Bhavanari, any query? I think some participants. Okay. We have got Bhavanari is there. Yes, please ask the question.
Sir, good evening and thanks for a very informative and encouraging presentation, sir.
Thank you.
I would like to know, in terms of etching, you have multi-layer etching. Starting of the presentation, you told that it takes around 2.5 to 3 months for fabrication. Some entire circuit. So, but when we have seen some etching parameters, like in between, you have shown some example like etching rate from 0.1 to 1 micron per minute. So, usually when you have many steps, how about the preciseness here?
Yeah, preciseness is, as far as etching rate is required, typically 0.1 micron to 1 or 2 micron, that is the requirement. And etch rate will not be uniform throughout the wafer because we are etching by plasma. Plasma itself is not uniform. If you see the fundamental of plasma, plasma is dense. Density of the plasma itself is varying across the wafer. Therefore, it is impossible to get uniform etching throughout the sample. But the variation we have to manage with a 5%. This is typically achievable, 5%. Better than that, it becomes very difficult. There are so many parameters we monitor, we optimize so that variation is less than 5%.
Thank you, sir. Thank you, ma'am.
Thank you. Ishika, any query in the chat box?
No, ma'am, there aren't any queries, but Sattam sir has asked, is it possible to see all the facilities in person to better understand the processes?
I always recommend you people to visit the wafer fab. There are many mini wafer fabs in India. As a team, you go there and see. For example, it is in Siri Pilani is there, Semiconductor Complex Limited is there. If you come to Bangalore, Sitar, it is there. There are many fabs. Fab means it is to small fab, not big fab. You must see all these facilities and you must understand the process. I always recommend not only etching, you must see lithography, you must see diffusion, you must see implantation. All the process you must see.
Right. And now many these labs, the clean rooms, they have opened these facilities and they want the students and the faculty, they must visit and see these facilities in person.
Yeah, which are the place near to you? For you, probably Siri Pilani might be near or SL Chandigarh might be nearer. You can plan. In fact, Siri Pilani provides a training on device fabrication. It includes lectures plus lab visit.
Right, right.
There's some 15 people in a batch, they take it. It's some nominal charges. You can apply to them and send it so that they understand complete process flow. They see the system. Now
Yes.
many IIT Bombay has started training this one. This will increase actually. The demand for trained manpower is very, very high. So this will increase. You can recommend your student to attend.
Right. We can coordinate for the industrial visits or.
Sure. Industry, whichever is near to your place, you have to choose.
Yeah.
In North
There is
India,
one.
Pilani is the one good place. SCL is nearby place. Even IIT Delhi has very good facilities.
Yes,
IIT Bombay
yes.
has very good facilities. You can approach.
Yeah. We used to take our students to IIT Delhi lab. Yeah.
That is good actually.
So there is Mr. Subedar, right?
Yeah, correct. Even now, IIT Monday, last year I visited, they have setting up very good lab. Very good facilities. Professor Satinder is there. We set up some equipment there. Last year I visited. Very good facilities. IIT Monday. Now almost all IIT they get 300 to 500 crores every year, and they are setting up very good shops.
Yes.
Yes, good evening, sir.
Yes.
Yeah, I am based in Pune. Just I wanted to know any fab nearby Pune to visit for.
Pune, Bombay is better. IIT Bombay is very nearby.
Okay.
They have very good facility, IIT Bombay.
Okay, sir.
Right. Ishika, any in chat box? Any query?
Oh, ma'am, there aren't any queries in the chat box.
There aren't. Yeah. It becomes a tiring day for everyone, I think so.
I know. Anyway, I managed to finish in time so that people are not disturbed for dinner.
But informative section, I would say. You can take it forward, Ishika.
Thank you so much, sir, for your insightful session on etching under vacuum conditions. Your expertise has deepened our understanding of its role in enhancing precision and efficiency in semiconductor manufacturing. We truly appreciate your time and your valuable insights.
Thank you, madam.
Thank you so much, sir. It was nice listening you for the 2 sessions, for the 2 days, I would say. And thank you for taking the time from your busy schedules. Thank you so much.
Thank you.
We'll be trying to connect with you soon for the other further collaborations.
Sure. Actually, I recommend so many R&D projects which is of low cost. So there you focus. You cannot think of buying equipment 10 crore, 20 crore and start some doing. Management also will not agree. There are many problems which you can address with a few lakhs rupee investment. And you can really contribute to the industry. This I always
surely
tell you
we will be connecting with you. Myself and my colleague, Dr. Anu, we will be connecting with you, sir. Right. Thank you so much, sir. So I request all the participants to please fill the feedback form, right? And the attendance is already captured from the Teams only. Okay. Thank you, everyone. So we will be meeting tomorrow again with the 2 sessions